Awesome. Um, so again, welcome everyone. We are essentially just having a fun little astrophotography session. I got together with a couple other students, and they have some incredible work some incredible machines and some incredible work that they've done. And essentially, I wanted to put together a little session where we could chat through it, kind of go over some basics and then also showcase like the different astrophotography that the students have been working on. Um, so yeah, feel free to jump in and ask any questions. I have at the end time for us to, kind of do a Q&A. If you want to wait, that's fine too. Because we'll have that. But essentially, that's what we're going to do today. There will be Oh, four other people doing presentations with me. And so essentially we'll switch off when it gets to that point. But I'm going to get us started because I think I have the most, not basic, I won't say that, but I have one of the most easiest setups that you can have. So just a little bit about me. My name is Tyler. I'm a junior going into my senior year in astronomy and planetary science. I do stargazing tours up here in northern Arizona, and I actually use the machine I'm about to show you guys on my tours because it can easily stack photos within 30 minutes, and I can show 3 to 4 cool astrophotography images in those public tours. Um, but I love space. I love astrophotography, not as much as some of these other kids, but hey, I shouldn't say kids. We're not kids. We're adults. Um, but essentially they got some really awesome rigs and some really awesome toys, which I don't have. But I'm also the event planner for this club, and so I've been trying to work on just trying to get more fun events like this going for us, available online. And that's my cat. I'm a cat person, so you want to call me the crazy cat lady, that is me. Um, so the machinery that I use is actually the Spera 2. This is not a real picture of my machine. I just pulled it off of Google because it looks the same thing. It comes with this measly little tiny tripod, but you can put it on a real tripod, and essentially it's a standalone astrophotography device. I say astrophotography device, but the proper terminology for the machine that I use is a smart telescope. And so, with these smart telescopes or astrophotography machines, they're pretty awesome because it's fully auto, self-stacking, and it does all the nasty work for you. Um, so some of the other students are going to actually go into detail about how they process and how they stack and how they image. I am just showing you a few cool pictures that I've taken with this machine that does it all for me. And so essentially, this machine connects to an app called Singularity. And within that app, it lets you basically, once the machine is on, you just hit a button and it'll auto align for you. And it's going to image the sky, make sure that it knows where it's at, and it's going to auto correct all of the stuff for you. Once it's ready, then you can essentially just select what object you want to view, and it will image it until it tells you until you tell it to stop. Or let's say clouds come into view. It will auto stop so that way it doesn't ruin the image that you put together already. Then what it does once it starts is it takes 10-second exposed images and it stacks them automatically for you. So when you pull up the Singularity app, you essentially have a finished image. Um, so we'll see that that's not the case with most astrophotography. You have to do the stacking yourself. But it is really a nice machine because it does it all for you and you just get the finished image. I personally use Lightroom or Photoshop for editing afterwards if I need to clear up some of the clarity and what have you. But really, quite honestly, I usually don't edit them very much. And those are both paid programs. They do have student discount pricing for all Adobe software. So if you're really into digital design, you can get it for cheap as a student, but they are paid programs. We're going to have a bunch of other resources, and a lot of them are free. So don't feel like you have to go and pay for programs just to get into astrophotography. I use it for professional and personal, so I pay for it. So I have just a couple images I wanted to share with us that have been taken with my machine. The first one is Bode's Galaxy, the Cigar Galaxy, and the Garland Galaxy in the top corner. This is a total of over 4,000 images stacked together for a total time exposed of over 12 hours. I love these three because you can get them close enough together in the same shot. I just didn't, what is the word? Center them properly. I hate that he's in the corner, but I got to get over it. The next one is like the most prominent galaxy, Andromeda. And this one is about almost 3,000 images, almost 8 hours. Andromeda's dead in the center with Messier 32 and 110 up and below it. And again, I like this one just because it's three galaxies for one. I if it doesn't make sense yet, I mentioned I do public tours. So if I can give them more for in one image, I like to. So I usually focus on objects that have things around them. So I can say, hey, look, we have three galaxies instead of just one galaxy being pictured. Um, my favorite nebula in probably, well, I wouldn't say favorite. One of my top three nebulas, the Lagoon and Trifid Nebula. And again, I love these two because they're close enough together that you can get the globular, or not globular, but open star clusters in between them with the two nebulas on their sides of the picture. I think they're just beautiful. And again, you get two nebulas in a nice picture. This was only about 1,300 images and about 3 hours. So what's really cool with my little machine is you could even do this for 45 minutes and you would have a pretty decent image. What it does is it just continues to stack over it. So it will just continue to make it more clear, more bright until it's done. And then my last favorite is the Flame Nebula, Horsehead Nebula, and the Lump Nebula, which is kind of that just little cloud. And this guy I've spent lots of time imaging because I think it's just a beautiful, beautiful little setup. But this is about 10,000 images for about 28 hours total time. But those are my images. I'm going to stop sharing my screen now, and I'm going to let the next person take over. And essentially, I just wanted to go first and kind of go, yeah, to start us off easy with one of the easier machines. Zach will take us away from here.
Hey everyone, can everyone hear me?
Yeah.
Awesome. All right, I will share my screen here. All right. Minimize this. Can you guys see this? Is this in the way here? I'll just put it down.
Yeah,
All
that works.
right. Okay. Hi everyone. I'm Zach Cooper. I'm an APS student. I currently work as a STEM instructor, and I plan on continuing with a career in science education after I graduate. I've been doing astrophotography in some way or another since December of 2020. That's when I first got a telescope and just pointed my phone camera through the eyepiece, you know. I am in a Bortle 8 zone, which is very high light pollution. So hopefully this can show you that astrophotography is possible even in very high light polluted areas. These are my two scopes here. The left is an 80mm refractor. Then on the right is a large 8-inch Schmidt-Cassegrain reflector. Everything else is the same here. This is an AVX mount. I'm just using a Nikon D810. This is like a 10-year-old DSLR, so nothing special there. I am guiding, so I have a guide scope and guide cam, and I'm using the ASI Air platform to control everything. So that controls my mount, camera, guiding system, any other accessories that you might have on your rig. And this just connects to my phone through an app via Wi-Fi. So that way I don't have to be out there with a laptop or anything. Before I get into my images, I wanted to show this. This is just a simulated field of view for each scope. So on the left with the refractor, you can see it's a much wider view. Compared to the right, it's much more, zoomed in, if you will. This is made using telescopius.com. If you put in the specs for your telescope and your imaging sensor, it will give you some useful info here. So in addition to the field of view in degrees, we also get the pixel scale, which is measured in arc seconds, essentially how much sky per pixel. The smaller that value is, the more precise your tracking and guiding has to be. So, the refractor is much more forgiving. If I have an error of only 1 arc second, that's going to be smaller than a pixel. You're not going to notice it. On the right, it's going to start creeping into other pixels. This will also give you your Rayleigh limit, just your maximum resolving power of the telescope. In reality, no one is ever reaching that because of atmospheric seeing, but it's interesting to have. Excuse me. Onto the solar system here. This is my only planetary shot of Jupiter. Planetary astroimaging is completely different from deep sky. For deep sky, you really need that exposure time to bring out those faint details. But planets are super bright, so you don't need that exposure time, but they're super small. So you really want a wide aperture to get that resolving power. And that atmospheric turbulence is going to blur out those tiny details. So to do planetary, you actually want a video camera to take tons of really fast frames and then only stack the best ones. With my camera, I can't do that. So this is just more of a traditional shot of Jupiter and the moons, but pretty cool to capture that. You can see the bands there and everything. Of course, this is our moon. The top one is my latest one, and this is just a cropped in version on the right. These are my early DSO attempts. Same M81 group that Tyler had there with Bodes and Cigar. That's 1 hour of integration. And then on the right, we have M101, and that's 4 hours of integration. It's a bit of a dimmer target, and that scope is also slower because of the focal ratio there. So it needed some more time on that one. Here's the Orion Nebula. My first shot all the way on the left was in 2021. I had no idea what I was doing when it came to processing, so it has some funky colors going on there. 2 years later, I shot it again, got about 4 times the integration time, followed a processing tutorial, and was really thrilled with that image in the middle there. But then another 2 years later, just this past summer, I reprocessed that same 2023 data. So I had learned a lot more about processing. I was more comfortable with the tools I was using, knew a lot more in terms of what they were actually doing to the data. And so it's literally the same exact data, just reprocessed. And so the reason I include this is to show that if you go out and you collect some data and you go and process it and it doesn't look great, that doesn't necessarily mean that your data itself is bad, right? It could just be that you need some more practice with processing. So definitely don't delete any old data that you may have laying around. Onto the North American Nebula. These are all processed the same way. The only difference is exposure time. So it doubles each time, starting with 1 hour, double it to 2, and then double again for 4 hours. So the more exposure time, the more detail you can really bring out there. As a general rule of thumb, to see a significant improvement in an image, you will have to basically double the exposure time. So even if you have like 8 hours on a target, to see like a really big improvement, you're going to need to double that to 16 hours. And similar thing here with the Andromeda Galaxy. This one doesn't double, but it goes from 3 to 5 to 9 hours. And on the 9-hour one, you can really see that extra data is bringing out detail towards the edges of the galaxy here, both on the left and right and kind of the bottom of that spiral arm there. Finally, I do have a comet shot. I just got this like a week or two ago. This was really tricky to shoot. It was super close to the sun. By the time I was able to align my telescope, I had to wait for Polaris and friends to come out before I could align it properly. By the time I did, I only got like 8 minutes on it before it dipped behind the trees there, and only 3.5 minutes of actual stackable data, which is on the right here. This is just two different processes of the same data. Um, this is not a great image, comet wise by any means, but it's still worth it to shoot because this comet in particular won't come back for over 1,000 years. Everything else in the night sky, you have your entire life to shoot. It's not going anywhere. But transient objects like this, definitely worth shooting if you can. Just as a basic setup routine, these things here are, I mean, kind of the very basics. If you're able to keep your scope out, um, all night, all day, maybe it's covered, then you won't have to do these things every time. If you're like me and you have to bring your scope out and set up every single night, you can't leave it outside, then you're going to be doing that stuff every night. One tip I do have is to bring your scope out early before you start imaging. This allows it to reach thermal equilibrium. Um, Scopes will cool down a lot, and when they do, there's going to be a lot of mechanical flexure, and your focus is going to become off as it's cooling down and as that metal is kind of shifting. So, just kind of a tip for that. Also, speaking of focusing, use a Botnov mask if you can. You don't even have to buy one. You can print out this pattern on paper and cut it out, and it turns your stars into this diffraction pattern down here. You can see on the left and right, this is what it looks like when it's unfocused. And then when you focus it, it brings that center bar right into the middle of that cross there. And that makes sure you just have perfect focus, as opposed to just staring at a tiny white dot and trying to determine if it's getting larger or smaller. It's a hassle. So definitely recommend using a Botnov mask if possible. Calibration frames. I'm not going to get too deep into this just because of time, but you should definitely take them. There's lots of tutorials out there for how to do them. These are the main three. Darks and biases correct for noise, essentially. Darks capture thermal noise of your sensor, and bias frames capture the base electronic read noise. So you definitely want to take those, and then in your stacking software, it will automatically remove that from your actual data. Flat frames capture the vignetting profile of your telescope as well as any like dust motes. And I'll show you a raw frame later so you can kind of see that vignetting there. And this is just kind of a flow chart of how all of that's organized and then subtracted from your data. I'm not going to get too deep into processing either. I believe Michael's going to go a bit more into that. I do have a time lapse of me processing my latest Andromeda image, just so you can kind of see how the data changes throughout the processing. These steps on the left here are going to be in every single workflow. Pretty basic stuff for that. Here's the raw frame I was mentioning, so you can see that vignetting around the edge. Taking those flat frames is going to remove that vignetting almost entirely. There's also a little dust mote here that would hopefully remove. So if you want to check this out on YouTube, it's a lot longer of a video, but I'll just kind of skip through this here so you can kind of see how it changes throughout the whole process. And so, it starts out as this, just a single pretty boring image. Stack a whole bunch of them and process them, and you can bring out all this really dim data. So if you want to get started, you can totally do it with your phone. I mean, these pictures, it's not the Milky Way or anything. This is under a full moon with like a 6-year-old phone. So, it's totally doable to get started tonight if you really wanted. If you do have a DSLR, you can totally do some lunar shots, maybe some short exposures on deep space objects as well. But the main thing you're going to want to do is to get a star tracker that's going to allow you to compensate for Earth's rotation. And that's just, the biggest thing that you can do to start getting much better images immediately. I also recommend going for easy targets in the beginning. Don't be like me. I started trying to get really, really dim targets in the very beginning, and it made it very frustrating. So go for easy targets. Shoot at zenith if possible. That's just a spot in the sky that's directly above you. Tends to be the darkest. You'll get the most contrast. Just makes things a lot easier. But yeah, that's about it for me. So I will bring you over to Michael here.
All right, let me get my screen shared here. All right. Can you see my screen fine?
Yeah. Yep.
All right, just want to make sure. All right, so my name is Michael. I'm a physics student here at ASU. This is me. This is my family as well. I'm getting a bachelor's in physics with a minor in data science. That photo on the left is me and my family at a Renaissance fair. My son is in the photo too. You can see him on the bottom left corner over there. I got into astrophotography about a year ago because I'm a space nerd. And I've been learning mostly from YouTube and ChatGPT. After I graduate, I plan to go on for a master's in astrophysics or planetary science. I'm leaning a little bit more towards planetary science so I can search for new worlds, very Star Trek. I'm hoping to share what I've picked up so you can start capturing some images too. This is my gear. For most of my shots, I use a C-Star S50, a Christmas gift my wife got me for celebrating getting into school. It's my main smart telescope for pointing, tracking, and capturing in TIFF frames. I pair it with an Aperture 2 moon and sky glow filter from High Point Scientific to cut the light pollution and boost contrast. And no matter what smart telescope you use, bring a portable battery bank so it can stay powered and collecting data all night. Then you can then you can stack and process everything later in Sorel. And it does come with this little tripod that's on here as well, just the standard C-Star. For target selection, picking a target can be really simple, a little fussy. Because Earth is rotating, your object won't stay up forever. It has a window. Take M31 Andromeda. Here in Massachusetts, it rises around 12 p.m. and sets around 8 a.m. So in theory, you got about 9-10 hours, but only part of that is dark and high enough to shoot. I use a rule of thumb, only image objects above 35 to 40 degrees altitude. For M31, that's around 6 p.m. At 42 degrees, at least right now at this season. So my process is open the Smart Telescope app, look for targets that will be above 40 degrees for a decent stretch. Check my direction. They rise and set so my house or trees don't block them, and then start the setup. Setup and calibration. I start by putting the scope on the tripod and taking it outside. I plug in the extended battery and route the cable so it won't snag when the telescope's loose. In the C-Star app, I level the telescope, run image sensor calibration, then do a flat frame on the iPad, which I set 70% brightness on the white screen laid over the lens. Once that's done, I frame the target, tweak my settings, and start to capture. I usually stay with it for the first 5 minutes just to make sure that it's tracking and not dropping a bunch of frames or anything. For data management, after about 4 nights of shooting, that's what I generally do. Not everybody has to do that, especially with a C-Star. It's just my preferred method so I can get the most amount of data and get a really high quality image. I start to import. I always capture in TIFF on the C-Star, so I can do the stacking myself in Sorel instead of using the telescope's auto stack. The scope saves both JPEG and TIFF, but the JPEG images aren't useful for processing, so I delete those and select all TIFFs and move them to my external drive. Once they're backed up, I start the edit and stack workflow. So getting started in Sorel, and you can see I have a little video over here so you can kind of see what's going on while I talk about this. For Sorel, I'm going to try and go into some detail, but I don't want to take up too much time. When you first open Sorel, it's important to set your working directory each time. This is where all your processed and stacked images will be stored. I highly recommend creating a subfolder in a location you store your photos, something like processed, and setting that folder as your working directory. When you're done editing, you'll want to delete the contents of that folder. Sorel typically creates nearly double the number of files in that original photos you took. Sequence. From what I understand, and I'll admit, I didn't read the manual, its job is to rename all the images, arrange them in the correct order for stacking, and that's about it. I do know it's important to always check debayer. You can see that right there. Registration. Next, you need to register the images. This process aligns the images using the stars so that they all match and they aren't stacked yet. Select registration under the registration method. choose global star alignment, deep sky, then click the small gear icon to the minimum star pairs and select the 3-star icon. This will highlight the stars the program can detect. If it shows more than 35, you're good to go. If it's fewer than 35, you need to adjust the settings to increase the number. Once that's done, click Go Register to begin the process. Usually it'll take a couple minutes depending upon how powerful your computer is. Stacking. This is the next big step and will take the longest to process. Click on stacking in the top tabs. Method, average stacking with rejection, normalization, additive with scaling, pixel rejection, winds rise sigma, clipping, weighing number of stars, leave everything else default settings, then select start. And again, you can see that little sample over here on the side. After stacking, the next step is basic editing. I follow a simple workflow since I haven't taken the time to learn more advanced settings in Surreal. I always start with color calibration, photometric calibration. This calibrates the images based on the object you captured. Since I shot M31, that's what I entered, and it made slight color adjustments and rotated the image to the correct orientation. Next, remove any green noise, which there's a setting in there for being able to do that. Crop the image however you like. Then apply Anash transformation. I'm going to say I don't know how to say that properly. Use this carefully, adjusting it only until the light from your target becomes visible, and balance that by adjusting the black point so that the image doesn't become too bright. Finally, perform a histogram transformation. I adjust the dark side first until I reach a clip percentage of about 0.009%. You don't want to go higher than that. Then I adjust the slide until the results look acceptable. I will add a clip in the next video that you can watch. And this right here is that clip. Anyone who wants to access the presentation afterwards, you can feel free to watch this. I probably won't sit here and allow the whole thing to play. You can notice my photo is blue in there versus what it originally was in some of the other slides. That's just because I had to backdate the software version of Surreal that I had. I had a newer beta version and it was giving me some problems. The next I go to Graxpert. This is another free software that I use as well. Graxpert is fairly straightforward. I just go down the list and you can see that list right here off to the left side. Background extraction, denoising, saving, which I usually do in 32-bit TIFF to bring into Gigapixel. And this is Gigapixel. Gigapixel is a paid application. It's pretty straightforward as well. It's useful for my needs, but it may not be necessary for everyone. After loading my image, I usually select the art and CG model since it tends to give the best results for this kind of work. You can toggle the eye icon highlighted in yellow to compare the original image with the enhanced version. I don't know what happened to my photo on here. I originally had it highlighted properly. The little eye icon's all the way down here, and for some reason it drifted upwards. Next, I go to Adobe Lightroom. I'm not going to go into detail here because there are hundreds of videos online that cover photo editing in Lightroom. If you're an ASU student, you can get Lightroom and other Adobe applications for free through ASU dashboard by selecting My Apps, where you'll find Adobe Suite available. Went backwards there. Okay. Yeah. Summary. All the applications I've shown you are easy to use and beginner friendly. I'll link the video I used to learn Surreal and the settings I've demonstrated. If you're interested in getting into astrophotography, go for it. The universe is incredible. Everything we are, sorry, I'm a little sick, so I'm still trying to get over that. And everything we see out there feels like art. We're lucky to live in a time when you can look up, capture these objects in detail, and actually study them. As Steve Hawking once encouraged, keep your eyes on the stars, try to understand what you're seeing, and stay curious. And these are both the links right there for everything that I used. And then I'll go ahead and show you quickly some of the photos I've taken here. Let me move Anuj here off to the side. There we go. So this is one of the first images I've captured on my telescope. This is M38. This is after editing everything on there. I probably only spent maybe one night shooting this. And let's see here. I have a couple photos of the moon on here as well that I took through the sea star. That's Betelgeuse. We have M42 as well here. This is a more unedited version of it color-wise. And I have NGC 281 Pac-Man over here. The Pleiades M45. And Monkey Head NGC 2175. NGC 2903 Barrel Galaxy M53. This is once I actually started to learn a little bit more about Adobe and finding like the correct settings on gigapixel. You can see like, a huge difference in photo quality afterwards. And then we have M106 on here as well, M13. And this is my latest photo other than Andromeda that I did. This one took me, I think about 4 nights, 5 hours of capturing each night. This is NGC 6992, and it's probably about one of my favorite images I've done so far. Then we have Andromeda as well. This is a photo that I took for this demonstration, everything that I used throughout the video. And that's about it. So I'll go ahead and pass it off here.
Hi, can you all see my screen?
Looks good.
Yeah.
Yeah, so I'm Anuj, and the image that you see here in background is my current long-running project. Don't ask me how many years. I've been like trying to finish this project for like 2 years now. So it is a nebula called Spaghetti Nebula. So a little bit about me. I am current master's students in electrical and electronics engineering here at ASU. And I started doing astrophotography in 2015. And before coming to ASU, I was working for Indian Space Research Organization. So I have seen some of this stuff actually put on satellites and satellites working in the space and stuff like that. And
I'm
basically,
sorry, I don't mean to interrupt you, but you have it on speaker notes, so it's kind of
oh,
it's
okay.
blocking half of it. So I don't want you to
Okay. Yeah.
keep going on that. There you go.
Yeah.
Sorry to
So
interrupt you. I apologize.
No worries. Yeah, so my journey in astrophotography started with a bunch of friends sitting on the terrace and a camera and Perseid meteor shower, along with the accidental photo of Milky Way. So this is how it is for me. So in 2015, I started with just a DSLR and ball head tripod. And in 2016, I added a shutter release or an intervalometer to it so that I can take star trails and Milky Way pictures without interrupting. And in 2017, I got my first telescope, which is a 6-inch reflector. Along with that, I got a German equatorial mount to track the sky, and it had a motorized RA axis. I did some astrophotography with that setup for about 3 years. And in 2020, I upgraded my mount to both the axis motorized so that I can computerizedly track the targets and use go-to function. In 2022, I got my first astro camera, that is ASI 1600 Pro, along with wideband and narrowband filters, and 120 which is a guide camera, and 4-inch refractor from William Optics. And finally, in 24, I got a one-shot color camera, that is ASI 533 MC Pro. So this is how my current setup looks like. In the first image on the top, the black tube, it's a 6-inch reflector scope from Skywatcher. And this is a filter wheel of having 7 positions where I can put my wideband and narrowband filters. And the red is my Astro camera, which is 1600 Pro. Other than my cameras and telescope, I use off-axis guider for tracking, and I have autofocuser to focus my scopes middle of the night. And in softwares, I mainly use PixInsight for processing, SharpCap Pro, APT, or Nina for image capturing, and PSD2 for tracking. One of the most important things when you are doing astrophotography, especially deep space astrophotography, are the filters. I have SHO 3 nanometer narrowband filters from Entila, and wideband filter from ZWO. So to begin with in astrophotography, you can just start with having a camera and a tripod. Uh, you need to just have DSLR camera with lens or a telescope and a tripod. And if you can afford it or if you can get it, a shutter release or intervalometer. And with this basic setup, you can do star trails, Milky Way shooting, lunar imaging, and landscape imaging with night sky. Basic software needed for processing these images, Photoshop, or if you don't want to spend a lot of money on getting Photoshop, then you can use Gem. And for stacking all these images to make star trails, you can use Starstacks, which is a free software. These are two images that I've taken in 2017 and 2019, respectively. Both of them are stacked images, star trails. So the one image on the left, it is total 146 frames stacked together. Total time elapsed is about 1 hour and 5 minutes. And per image exposure is about 20 seconds with 400 ISO setting at f/4 focal ratio. So the equipment that I've used in both the images is similar. I had a Canon 650D DSLR camera with ball head tripod and a Neewer intervalometer. And software I used is Photoshop, Lightroom, and StarSec. So the image on the right that you see, it's a composite of two images having different exposure because for a background image, I needed to take longer exposures to get the star trail. But with the longer exposure, my foreground was getting overexposed. So I took two separate shots, one for the background and one for the foreground. And in Photoshop, I merged both of them to get the composite image. Uh, I don't know if you can see anything in this image, but there is a deep space object in this image. Can anyone tell me if you can see anything? Is
Just
anything
I see
visible?
nothing.
Yeah, it looks
I
black.
see a dark nebula.
Yeah, some of you might see some stars or some spots in it. So let's see what's in this particular image. So it's the image of Rosette Nebula. It's completely stacked image. After hours of exposure, it's just not processed. So that is the only difference between this image on the right and the image on the left. Both are same image. It's just that left image is not processed. It is not stretched. The right image is stretched. The data and everything is same. So if you are getting into astrophotography after stacking, if you don't see anything, don't panic. The data is there. And as Zach also said, you can reprocess the data after learning processing after years, and you can get better image with the same data also. So I'll now delve upon some of the equipments that are important if you are going into astrophotography, especially deep space astrophotography. So one of the most important equipment for any kind of photography is a camera or a imaging sensor. In astrophotography, we have mainly two kinds of cameras. One is one-shot color camera and another is mono camera. One-shot color camera, as name suggests, it's a color camera, and it gives you a simple workflow in imaging as well as processing, because in imaging, to make a color image with one-shot color camera, you don't need to have any kind of filters. One-shot color camera in itself has filters, which is known as Bayer filter array. On the image in the center, you can see. So the gray area is a monochrome sensor, which every camera will have. On top of that, every color camera will have a Bayer pattern, pattern which is made out of red, a green, two green, and one blue filter. So here on the center, you can see how this in array of 4 cross 4, total 16 pixels, only 4 pixels have red filter, 8 pixels have green filter, and 4 pixels have blue filter. And when you combine all of it, you get a color image. Now, what are the cons of a one-shot color camera? It requires longer integration time due to loss of pixels. Because in array of 4 cross 4, only 4 pixels are getting a light from red pixel, 8 pixels getting image from green filter and 4 pixels getting image from uh, four, uh, uh, 4 filters. So it's not a very good combination with the narrowband filters. Now, coming to mono cameras, each pixel is getting greater light compared to one-shot color camera. So you can do with shorter integration time. What are the cons for it? It has a complex workflow because you now need to use multiple filters to get a color camera. And in processing, you need to stack all those different images and process them further to get a final color camera. Also, you need to have filter almost always, either RGB filters or narrowband filters. Now, who wins between the one-shot color camera or monochrome camera? Both of them. It depends on your use case. What do you want to shoot? If you want to go for broadband targets, or if you want to go for very simple workflow, I would suggest go for one-shot color camera. And if you are going for deep space targets, lots of nebulas, I would suggest go for monochrome camera. Now, what is broadband and narrowband imaging? On the right, you see a curve where you have a blue region, green region, and a red region. Using RGB filter, you can get the light on that wide area of spectrum. That is called broadband imaging. So broadband imaging captures light emitted at many wavelengths. It is mostly used for stars, galaxies, planets, and many of the nebulas, especially reflection nebulae and dark nebulae. What is the issue? It is very prone to light pollution because LED lights or the white lights emits in the all the spectrum. So it is very prone to light pollution. And if you are shooting from the light polluted area, broadband imaging can get very tough. Now, narrowband imaging, it captures light emitted at a particular wavelength. So mostly nebulae, which are emission nebulas, and galaxies are the narrowband targets. We use narrowband filters such as sulfur 2, hydrogen alpha, or oxygen 3 to help us with the light pollution and to capture that particular small window of photons. So on the bottom, you see 2 images of the same target. On the right, it is a RGB, it is a broadband image of the Trifid Nebula. On the left, it is just a single image of alpha, H alpha. So here you can see at the center, the red part, it's visible in both. So that particular region of nebula is emitting light in broadband as well as in H alpha. But at the bottom, the blue region, only you see that in RGB. It's not visible in H alpha. So that particular region is not there in H alpha. Now, this is one of my images of Rosette Nebula. It is a SHO false color composite. And so total imaging time is 22 hours and 15 minutes with H alpha for 8 hours, O3, oxygen 3 is for 5 hours, and sulfur 2 for 7 hours. And I have used ASI 1600 with paired it with the William Optics Redcat 51, which is a 4-inch refractor, and it is processed in PixInsight. So this image is made out of total 3 separate images, H alpha, O3, and S2. So any of the color images, they are made out of 3 channels, R channel, G channel, and B channel. So we have to map this monochrome images to R channel, G channel, and B channel to get a color image. So SHO palette is also known as Hubble palette, in which we map sulfur image to R channel, H alpha image to G channel, and O3 image to B channel. And we get this kind of image after that. So this is another image of mine, which is a Orion molecular cloud complex. It is a 2x2 mosaic of Orion molecular cloud complex. And I have used RGB image and used HSO composite on top of it. Total integration time I have used is about 38 hours and 51 minutes. The complete image is processed in a PixInsight, and it is with a 4-inch refractor. So this is color image of Trifid Nebula, where I have paired RGB broadband data with H alpha data, and total integration time is about 21 hours and 43 minutes. And this is another 2x1 mosaic of Heart and Soul Nebula. Total integration time for Soul Nebula is about 18 hours. And for Heart Nebula, it's about 13 hours and 50 minutes. Let's talk about electronically assisted astronomy. So it's a mid ground between full-fledged astrophotography and a visual astronomy. You can use a computer and few of the software which live stack your images, and you can basically show it to people or just have a very quick gratification of observing faint objects. Uh, I think I'll show you my images in better resolution now. Yeah, is the screen visible?
Yeah.
Yeah.
Yeah, so this is a 2x1 mosaic of Heart and Soul Nebula. So yeah, even if I zoom further, like there are lots of details and basically there is very less noise. So this is Orion Nebula over here. This is Running Man Nebula. There is lots of H alpha activity, H alpha cloud all around the molecular complex. This is Horsehead, and this is a Flame Nebula over here. This is a Saturn region where you see Crescent Nebula, which has H alpha and O3 emission. This is Rosette Nebula. This is Trifid. This is Tedport Nebula. It's a very wide field image, so we can't see tadpoles over here. This is Markarian's chain. Basically, there are lots of galaxies. All these are separate galaxies that you see over here. And it's a complete chain in Leo constellation. This is Lobster and Claw Nebula. Lobster Claw Nebula and Bubble Nebula over here. This is M45 Pleiades with a lot of wisp around. I think my part of presentation is done. I am going to stop sharing now.
Would you mind going back to the one with the string of galaxies?
Yeah, sure.
It looks like you might have caught some lensing in that.
Oh, I don't know where. Hmm.
Is that not that wouldn't be gravitational lensing, would it? Like that looks like the same galaxy three times.
I don't know. I don't know. I actually don't know. I need to read up on that.
What is the name of that?
It's basically it's a chain of like galaxies, and they call it Markarian's chain, but I don't know if individual galaxies are named or not.
Okay. I'll look it up because that's
Okay.
really a very nice picture.
Yeah, Markarian's chain is a very interesting object to picture usually. Anything else?
I had a question about those images that you showed a comparison of the really dark one and the one that was much brighter. You said those were
Yeah.
the same images, just it was just processing that changes that?
Yes. So basically, all the data, if you plot a histogram, right, of the dark image, all the data is towards the left. So what you have to do when you are processing, you have to stretch that histogram to the right, and uh, that is how you get the bright image. So let's see, if you have suppose a 280, 256 pixel. Sorry, if your brightness is quantized into 266 steps, so your data is in the black image, it's from 10 to 15. Now to stretch the histogram, you map it that 10 to 15 to 100 to 200, something like that. So basically, you scale the histogram, and that is how you get the bright image.
Oh wow. Cool. Thank you for sharing.
Yeah.
All right. I think it's me now, right?
Yes.
Yep.
Okay. Is that easily visible?
Yes.
Okay, cool. So I'm Evante. I'm a I'm not sure what year I'm in, but because this is my second bachelor's, but I'm in the APS degree. This is a picture that I took of Andromeda. I don't think it's the integration time is that long. It's probably like an hour, maybe two at most. I just spent a lot of time on my tablet one night applying a bunch of different filters and stuff, using I don't even know what it was, maybe Snapseed or something, or maybe even Google Photos or possibly both. And I just messed around with it with a bunch of, different processing things and filters and whatnot to get it to a point where I was like, oh, this doesn't look at all like what it used to. And yeah, so the equipment that I have used and still have, the first telescope that I got was a Unistellar Equinox 2. I didn't get it to get into astrophotography. I got it to basically do citizen science, and I'll talk about that a little bit more later on. But, sometimes you feel like actually taking pretty pictures, and so I ended up with a Dwarf 2, a Dwarf 3, both from Dwarf Lab and a C-Star S30, which is the one that I use the most now. They're really nice because the Dwarf 2, Dwarf 3, and S30 are very small, and so in particular, they're very good for like taking them on airplanes. I can just fit them at the bottom of my backpack, and I don't really have to worry about anything with respect to that. This picture that's the Unistellar scope with the backpack on the bottom right and a little stool that I used. And then the cat in between the tripod legs is one of the neighborhood cats that we feed. Um, I find astrophotography a great way to bond with my cats. We have five that live inside. And what I'll do is basically put them into a carrier and bring them outside, and then I'll set up my equipment. And they absolutely love that. They love being outside, but I can't let them roam free when I can't see and they can. Plus, they'll be liable to like run into the neighbor's yard and whatnot, but they really love it. And, they always look forward to it. And when they hear me like setting up the backpack for the Unistellar or like zipping up or unzipping the case for my Sea Star, they'll come running and start complaining. So it's a lot of fun. So I thought I would talk a little bit about solar photography, which is a bit different from what everyone else talked about. Um, for one, the sun is extremely bright. It's something like magnitude like minus 26.8 or something. So the process is a bit different. There are a couple interesting things that you can do. I think anyone that does solar photography likes to take pictures of the sun when it's closest and then compare it to when it's farthest. It's closest sometime during the summer solstice, maybe like 1 or 2 weeks after, and then it's the reverse for when we're farthest. That happens sometime in early January, a couple of weeks after the winter solstice. Solar eclipses, of course, and you might see every now and then someone gets the news for an amazing picture that they took of something in front of the sun. In fact, just today I was scrolling on my phone and the algorithm showed me an article of someone that had uh, basically taken a picture of someone skydiving in front of the sun. I read that it took a couple attempts, but it's called The Fall of Icarus. So if you can look that up, I'd highly recommend. It's really amazing. Um, yeah, but there are also pictures of people have taken pictures of the sun with like a plane moving in front of it. Sometimes people get lucky during a solar eclipse and they'll catch something like that, or birds, stuff like that. The process is slightly different. I've noticed that finding the sun is not very easy for an algorithm, which baffles my mind because, for us, it's just like, oh yeah, the sun is right there and it's super obvious. But that means that normally I manually point my scopes. But of course, before you actually point your scope at the sun, because the sun is extremely bright, it can damage your electronics if you don't have a filter first. So basically, these pictures on the right are like a step-by-step process. Um, it's sort of like left to right, top to bottom. So you can see the solar filter inside the little case that it has. And I always like to just look at the sun myself through it because sometimes you can even see tiny little sunspots. So that's a picture that I took, and that little orange dot is the sun. And of course, you can see the ground and the phone and the reflection. This is the S30 that I mostly use. I think most of those smart telescopes that you get now, especially the small ones, will come with a solar filter. I don't think that's as common for the larger ones. Like I know for Unus telescopes, you have to buy it separately. Um, and then that second or that middle image on the bottom is basically a screenshot of me trying to find the sun, trying to center it in the field of view. And then the last one is what it looked like on that day. I think this was taken last week, maybe the week before. You can easily see some sunspots, and the whole process probably took like 10 minutes from going out the door to coming back in. And it's really cool. You might need to take care that your equipment doesn't get overheated because that's very easy. Obviously, you can't put it in the shade because if you put it in the shade, then the sun is no longer visible. Um, so yeah, just be a little aware of that. And there are also dedicated solar rigs that you can buy. I think that might be the easiest way to use an H-alpha filter because for various reasons, you can't use a normal filter that you would for like deep sky imaging. But those dedicated solar scopes are pretty pricey. I'm not gonna lie. They're like maybe the cheap end is probably like 700, 800, and then it can easily go up to like 10,000 or more. Um, all right, so this is my take on perihelion versus aphelion. Perihelion. I remember that day was very cloudy, but not so cloudy that I couldn't see the sun. So that's why you see this like sort of haze around it. Um, both of these, I think, were taken within maybe 2 hours of the actual instant of a perihelion aphelion. Um, and they're both from this year. There are some sunspots in the perihelion, but they're kind of hard to pick out because, the clouds. And there's a few more visible in aphelion. And so I made basically a GIF to show the size difference. It's a little difficult, I think, unless if you look at the edge, keep your eye on the edge, and then you'll notice that when it grows or shrinks, the edge moves, which is pretty cool, I think. Yeah, so this was a picture from me going to Montreal, April 2024 for that eclipse. You can see a lot of astrophotographers in here. M Most people there, were not there to image, but a couple of people were. And then on the right, I have something that I built from my images that I took with my Dwarf 2. I think the whole affair lasted, oh gosh, we're probably there from like 8 to 4. Yeah, 8 a.m. to 4 p.m. The one in the center that is the, moment of totality, I actually had to extract that from video because my process was basically I set up my Dwarf 2, figured out, well, first I had to figure out where we were going to sit. We're going to be there for a long time, so it had to be close to the bathroom. I wanted a park bench so that we could sit down, on somewhere nice. And obviously, I had to make sure that the sun wouldn't be blocked by anything over the course of the eclipse. So the edges were stills that I took, every like, I don't know, 15 minutes or something. I would just quickly snap a shot. And then, like I said before, the moment of totality, I had to extract a frame from a video that I took. Um, yeah, so one project that I've been doing for a while is sometimes I'll read about an object that's very interesting, especially from, the phone algorithm will tell me, oh, scientists found this thing, or a paper came out about this thing, and I'll read it. I'm like, wow, that sounds really cool. Where is it? I want to take a picture of it. I want to look at it. And so here are five or so images of things that I find very interesting, but if you were to look at them through a telescope, it would basically just be a point of light. So this is HD 162826. This is really cool because scientists have figured out that it was born from the same molecular cloud as our sun. So I sort of think of it as like our cousins, I think, because like the Earth is the sun's child, and maybe that star is like our aunt or uncle or something. I don't think it has any confirmed exoplanets, but I think scientists think that it probably does have some terrestrial planets, basically due to the metallicity in the spectrum. Um, and there are a couple other stars like this, or rather star candidates. I'm not sure anything has been confirmed. This is in Hercules. Yeah, only about 110 light years away, which is, when you think about it, kind of close, especially because our solar system is only about 20 galactic years old, right? We've only gone around about 20 times. Um, so yeah, it's looking at this, I think it's always interesting just to think that maybe there's someone there that's doing the same thing with us. Like maybe there's scientists who figured out, oh, this star was born from the same molecular cloud, and they're doing the same thing. This is Andromeda's parachute. It's that very, very small star next to the bigger one to the top left. This is located in Andromeda. It's If I had a better scope, you would have been able to tell that this is actually a quasar that's being gravitationally lensed by a large galaxy. And it creates four images. One of them is a bit fainter than the other three, but the other three are pretty bright. Um, this was part of my quest to see if I could actually see something gravitationally lensed with the equipment that I have. But like you zoom in a lot and you can't see it, so I just don't quite have the resolving power that I need. Um, but I think it's still interesting to know that, the thing that you're looking at here is actually an instance of gravitational lensing. And of course, it was very difficult to figure out exactly which of these points of light was the object that I was looking at. So I used astrometry.net. You can basically feed it a photo that you've taken, and it'll analyze it, figure out if there are any interesting objects, label them, and then that gives you a reference image from which you can compare to your own. Personally, with my brain, I find it a little hard, so this one probably took like 10 or 15 minutes to make sure that that tiny little point of light is the one that I was interested in. And a lot of these pictures are basically going to be like that. So this is Gaia BH1. BH, you might know, but stands for black hole because Gaia can only see one of these objects. Um, and I picked this one particularly because it's one of the closest known black holes. It's stellar mass black hole. The other object, the star, is roughly the mass of our sun, maybe a little bit smaller. Has a very similar temperature, and the black hole is also stellar mass black hole. It its mass is about a little under 10 times the mass of our sun, which means that its Schwarzschild radius is really, really small. It's about 17 miles. So like after this meeting, I'm gonna go visit my parents. And they're definitely more than 17 miles away. So by the time it takes me to get there, I'll basically have traversed the whole length of the event horizon of this black hole, which is kind of crazy. Um, and there are some other candidate um, stellar mass black holes that they're close by. Not sure how many of them have been confirmed, but there's like Gaia Beach 2, Gaia Beach 3. I think this was the probably the first one that was discovered by Gaia. Um, and it's an Ophiuchus. I hope I pronounced that right. This is 3C273. I think this one was the first one of these images that wasn't taken by my Unistar. I think this was one of the dwarves of the sea star. It's really, really far away. It was first discovered, I think, in the 70s. Um, it's the first quasar that was ever discovered, and also the brightest, which makes sense, right? Because it was discovered quite a while ago. And you might know the history of how it was discovered, but basically they, took spectra of the thing that they're imaging and realized, wait, like there's a lot of redshift here, so it can't be a star. Um, but yeah, this is located in Virgo. Um, Possibly one of the farthest things that you'll be able to see through a telescope that you can just buy off the market, for consumers. Um, it looks just like a star, but it isn't. And I find that really interesting. The supermassive black hole at the center is about 900 million times the mass of the sun, and yeah, it's really, really far away, about 2.4 billion light years. Um, Visual magnitude is almost 13, so very faint, but still well within the realm of what you can see through a telescope in your backyard. This is a picture that I took, I think, with my Dwarf 3 of the galactic center, which is very close to the spout of the Sagittarius teapot, if that's how you see Sagittarius. So this is mostly a summer target. Now it's hard to pin down exactly where it is, because the galactic center is it's not small, right? Um, but I'm sure most of you have seen pictures of the Milky Way, and you can see that a lot of it is obscured by clouds of dust and gas. Unfortunately, the center of our galaxy is also obscured by a big cloud of dust, but somewhere in here, there's a supermassive black hole, I think about 4 million times the mass of the sun. Um, and if this were taken in the radio, then it would be much brighter, right? Okay, so I thought I would talk a little bit about citizen science as a plug for what I like to do. It's a bit different from astrophotography, but it's very related. Like I said earlier, I got into it with unistellar scopes. I honestly believe that it's probably the easiest way to take data and contribute to citizen science. Um, Starting at the top left and then going right, there's a variable star. You can see the light curve, hopefully. You can see that it's kind of wavy, like a sine wave, and it dips down, gets brighter. So typically we'll get requests from some researcher somewhere. They're like, oh, why don't we use, people that have unistellar scopes, and they're located throughout the world, both hemispheres. Some targets, some events, especially asteroid occultations and exoplanet transits, are only visible from some parts of the Earth. But the easiest way to get into it is definitely to start with cosmic cataclysms. That's mostly stuff like supernovas, novas, and that's actually how I got into it. The second image is supernova 2023 IXF. You might have heard of it. I think it was discovered in M101. It was something like the closest supernova to Earth in a long time. And yeah, you can see the light curve there of especially early on, it blows up in brightness and then it slowly tapers off. And yeah, that was, oh gosh, yeah, I guess 2.5 years ago. And then the third one is probably the one that I've taken the most images of for citizen science, TCRB, which is predicted to nova any day now. Um, I'm predicting next year just because that fits nicely with the 80-year recurrence pattern, but it's only like 3 or 4 data points. Um, but yeah, that's definitely a target that a lot of people keep their eyes on. So there's a ton of data on that. And then on the upper right, this is a light curve of an exoplanet transit. But what made this exoplanet transit interesting is that the planet is disintegrating. So the light curve is going to be a bit different. Um, it's not going to be that sharp like drop down and then rise like you would normally expect because the mass is smeared out over a much bigger area than just the radius of the planet. And yeah, sometimes you can get your name into a research paper. This is a screenshot of the front page of one of those. Um, I don't remember which observations of mine they used, but yeah, it's always exciting when that happens. Um, and there are other ways to do citizen science too that don't involve actually taking data and sending it to someone. There's the Galaxy Zoo and Black Hole Hunters. I think those are both basically programs where people will look at images and then classify them. Both of those are on Zooniverse. And yeah, that's that's what I have.
Awesome. Um, Thank you, Evante. And that brings us, our last slide in the presentation is just a slide that has a page full of resources. So if you want, that's more for you to go and use on your own time, and you can grab all the different free resources that are available. Oh, so I should put on the video. Thank you all who presented. I'll kind of give us a few minutes. Anyone can ask some questions, and whoever feels like they can answer it the best, I guess, can step in. Oh, go ahead, Tim.
I noticed two terms. One of them was exposure and the other one was integration. I'm very familiar with exposure as far as photography goes, but what's the difference between that and integration?
Integration is just like how much total exposure time. So if a single photo is maybe 1 minute or 2 minutes, then you stack 30, if you stack 30 2 minute frames, then your total integration would be an hour. So they're somewhat interchangeable in that regard. Integration is just like total exposure time.
Makes sense.
So you can also have like a single photo, single frame with the exposure of 30 minutes, but we don't do that in astrophotography. We usually break it down in shorter exposures because the longer you have a single long exposure, the higher the noise will be. So you take shorter exposures, and you stack them.
Thanks.
Awesome. Any other questions?
Oh
I
yeah,
think you guys all did amazing, by the way.
I have one more question for Evante. That
Yeah.
What's up?
That image, well, the data that you got on the exoplanet transit, was that you got that data yourself?
Yeah, so the full light curve exists, but the reason why I didn't show that one is because I think I was for that night, I think the only person that caught the ingress. Um, and that's because a lot of people that were imaging this were not on the right part of the Earth when the ingress happened. And I know there are other people like in the Bay Area or the West Coast that were shooting as well, but sometimes clouds get in the way, or maybe the target is off center. Um, so yeah, that was all taken with my telescope. And exoplanet transits usually last a really long time. So sometimes it's a case of set it up, let it go, check it on it later, and then upload. But yeah.
Yeah, that's amazing.
Oh, I think you guys did a really good job. I'm just like kind of blown away by some of the pictures and filters and different things you guys do. I need to step up my game. Um, well, cool. If there's no other questions, I know we went a little over, but I think it was well worth it. We had, I mean, so much good information. So I really appreciate your guys' time. Um, yeah, all the time you put in. I'm really, really impressed. So thank you. The video will be available, so if you want to review it at any point, give us like a few days, and it'll be posted on our YouTube. Michael will send out a little announcement with that. And then one note with that is we'll also include the link to the presentation. So if you end up losing it between now and then, you can always go to our YouTube page and it'll have that link.